In this video, we're going to take a look at the exam 4 review. So this is a practice test for exam number 4, which is on chapter 4. And so I'm just going to go through these problems at a fairly quick pace so that you can be as prepared as possible for the exam that you will be taking on chapter 4. Question number 1. Given the function, find g of -4. So g of x is equal to 1/4 to the power of 1 minus x. We want to find g of -4, so we're just going to plug that number in for x. So g of -4 is equal to 1/4 to the power of 1 minus -4. So be careful with that negative sign that we are plugging in. Because it's following a minus sign. So you want to be careful whenever they like to do that. They like to give you negative numbers and then have you raise them to, powers of 2 or 4 or whatever, which makes the negative sign go away, or have you plug it in after a minus sign. And then you have to be extra careful with the double negative. So this is going to become plus. And so we're going to get 1/4 to the power of 1 plus 4, which is 5. And this one's kind of a big number. So to raise a fraction to a power, it's not as hard as it might look. You just apply that power to the top and bottom of the fraction. So you get 1 to the 5th power over 4 to the 5th power. 1 to the 5th power is easy enough. That's going to be 1. But 4 to the 5th power, I really don't know. Usually I'll be able to figure these ones off the top of my head. But, 4 to the 5th power is a little bit bigger than I'm used to having to deal with. So 4 to the 5th power is equal to 1024. All right, I guess I should have maybe known that. It's a power of 2. It's 2 to the 10th power. It's the same thing. So, all right. Question number 2. Use transformations to help graph the function y equals 2 minus 2 to the x power. Identify the domain, range, and horizontal asymptote. Determine whether the function is increasing or decreasing. So we're being asked to do a lot of things on this problem. The transformations that are occurring here, so you compare this to the basic exponential function of just 2 to the x power. So you keep the same base, but just keep it basic with nothing else there except for 2 to the power of x. And what's different between these two functions is we have this 2 out in front, which is really being added to the -2x, right? This is really, if you flip it around, it's -2x plus 2. That plus 2 is going to shift the graph up 2. And then the negative sign in front of the 2 to the x power is going to flip the graph over the x-axis, right? It's going to flip it over the x-axis, which again is the only kind of reflection that we studied. So when I say flip the graph over, that's the only kind of flipping that we could be doing because that's the only kind that we studied earlier. All right. And so those are the two changes I need to make to this graph. So the basic principle here is that you've memorized what the graph of just 2 to the x power looks like. And so an exponential function looks something like this. Yeah, okay, that's a pretty bad drawing, but it'll work. And there's an asymptote here on the x-axis to start off. And so that's your basic exponential graph. And, as long as the base is bigger than 1. And so we want to change it by flipping it over and then shifting it up 2. So that's the order we would do that in. So we're going to flip the graph over. And so it's going to look like this instead. The asymptote would still be here at the x-axis, but we'll flip it over the x-axis so now it looks like this. And then we'll shift it up 2. And so one point that you want to keep track of here is this point. It starts off at 0, 1. When you flip it over the x-axis, it will now be at 0, -1. And now we're going to shift that up 2. So it's kind of a funny thing that happens, but when you shift that up 2, it goes back up to 0, 1. So it's going to end up right where it started, except it's going to be flipped over. The asymptote also gets shifted up 2. So it starts off at 0. And now that's going to get shifted up 2, so it's going to be up here at 2. Right? So instead of being at y equals 0, it's now going to be at y equals 2. And then that graph is still going to look the same when you shift it up. So this is what our final graph is going to look like, something like this. All right, that's just a rough sketch. One thing I was going to say, the first thing we have to do, but I guess we don't have to do this first, but this will also help us with drawing the graph, is tracking where all these points end up going when you apply these transformations, right? So these are the points that are on the original function, right? 0, 1, 1, 2 is on the original basic function here. It's supposed to be a 2. Negative 1, 1/2 is right here. Where are all these points going to end up after we apply these transformations? So we're going to flip the points over first. So we saw what happened with 0, 1. When you flip it over, it goes to 0, -1. So flipping a graph over the x-axis, all that's going to do is change the sign of your y-coordinate. The x-coordinate will stay the same. It'll still be 0 like it was in this case. But instead of +1, we get -1 when we flip it over. And then we're going to shift it up 2. And what happens when we do that is we add 2 to the y-coordinate. So again, the x-coordinate doesn't change, but the y-coordinate's going to go back to being 0, 1. All right, so I hope this doesn't become an issue. In the past, I've had problems with this software starting to get laggy as I write more on the screen. And I'm a little bit worried about that because I have there's more to this screen than what you see here. So now it's been behaving pretty well. I got a new computer. The software seems to have been updated, but I don't know. It did kind of glitch on me there, so I'm a little bit worried now about that. All right, so we make the same changes to the other points, right? So we're going to take the point 1, 2. When we flip it over the x-axis, it becomes 1, -2. We just changed the sign of the y-coordinate. And then we're going to shift it up 2. And so when we do, we add 2 to the y-coordinate, and it becomes 1, 0. Right, so that'll be another point. So we can go ahead and plot these points. We have 0, 1. We have 1, 0. And save the best for last here. Flip this over. It becomes -1, -1/2. And then we're going to add 2 to that. So you can think of it as a decimal. Now, if you're typing this into Math Excel, it wants the answer in fraction form. But you can think of this as a decimal on paper and for graphing purposes. So think of this as -0.5. And when you add 2 to that, if you think of like money, -50 cents plus $2, right? It's going to be 1.50. In fraction form, that would be 3/2, right? Positive 3/2. So we're going to get -1, positive 3/2, which is 1.5, which is going to be about right there. All right, so that's the answer for this part, is these points here, right? Then we would graph it. Remember, the asymptote will be located at y = 2. That's a really important feature of the graph. So even if all you're doing is plotting the points, if you're not paying attention to where the asymptote is located, you might still get a graph that doesn't look right. So if you really want to have the most precise, best looking graph, you want these points, but you also need to be aware of where the asymptote is now located. All right. So what's going to happen here is going to the right, it's going to follow these points. Oh, okay, let me try that again. Follow these points, and then it's just going to really sharply curve downward as we see up here. Really badly drawn on my part, but I think I'm just going to leave it at that. Going to the left, it's just going to approach the asymptote without crossing or touching, and I kind of messed up on that. Now, what should not happen is reaching the asymptote like I did here and then going back away from it. What happens is the graph always gets closer and closer and closer without crossing or touching. But again, this writing tablet, it's kind of hard for me to do that very well. So, all right, so that's what our graph looks like. What is the domain? Once we have the graph set up, it's a little bit easier to figure out the domain. How far to the left? How far to the right? And for exponential functions, it goes forever to the left, right? And that's pretty clear here. But it also goes forever to the right. It's going to keep going down and to the right forever. And so it's going to go to the right, positive infinity. It's going to keep going forever. The range is a little more interesting. How far down? That one's pretty clear. It's negative infinity. I'm going to try to write that one more time. Negative infinity. How far up? Well, it has a limitation. It will not go past 2. So 2 is as far up as it goes. And it never, even though I've drawn it kind of badly here, it never reaches 2. And so we don't want to put a bracket on that because it never equals 2 either. It's always just below it. And so we use parentheses on that. All right, so let me try this. Oh, I don't actually, now that I think about it, I don't think this works. So my plan was to just scroll up, which I think it will do with the background, which is the test, but my writing probably won't move. I don't know. Let's see what happens. Oh, no, it moves with it. Okay, I was worried that the test would move, but my writing would stay right where it was. Thankfully, that's not how it works, so this is great. Okay. All right, and then the horizontal asymptote. So not only did we need that to have our graph drawn, I said that really weird, our graph drawn accurately, we also needed it to answer this part of the question. So the horizontal asymptote was at 2, and the equation for that is y equals 2. And is this graph increasing or decreasing? Well, to figure that out, we start from the left-hand side, we look to the right, and what's happening is the graph is just going to go down the whole way. Again, I kind of messed up here with the way I drew this, but it should be more like up here, and it's always heading down. It's always decreasing. And so it's decreasing. It kind of bugs me that it makes us actually describe where it's decreasing, because it's just always decreasing. Like, it's just, you can describe it as a decreasing function because that's all it ever does. It's always decreasing no matter what. But it wants us to describe where it's decreasing, and it wants us to do that in interval notation. And so it's from the very left-hand side, which is negative infinity, to the very right, positive infinity. It's just always decreasing from the very left to the very right. And so that would be how you would answer that part of it. All right. The last question on this page is solve this equation. Again, we have a base of 1/4 like we had for the first problem. That may not happen on the version of the test that you get, but 1/4 to the x power equals 64. This is still in section 4.1, so I'm not, at this point anyways, now with the test moving online, I've considered scrambling up the order of the questions just to make, to hopefully make it more difficult for students to like collaborate and cheat by working on the test at the same time. However, I haven't done that yet, I don't think. I'm sorry, I just had lunch and it just always, the digestion always gets me a little bit. So, all right. So what I was saying is these questions are in order of the material in the chapter. And so we're still within section 4.1. And in that section, and so for question 3 on the exam that you take should still be the case, the method that we had for solving these equations was to get both sides to have the same base. And then you just set the exponents equal to each other. So you shouldn't have to use logarithms here to solve this equation, but that is one way to go. You could solve this by doing a log base 10 to both sides of the equation. I'm going to use the what I think is the easier method, and the method that was intended here, which is to get both sides to have the same base. This one's maybe one of the more difficult ones to do that with, because you have to change both of them to get them to match up. I mean, again, you don't have to, but that's the easiest way to do it. And the way we're going to change both of them is to make both of them have a base of 4. That's the easy thing to do here. 64, we can write that as 4 to the 3rd power. Right? And then 1/4, I can flip that base over. The rule, however, is if you flip a base over, you have to change the sign of the exponent. And so the exponent becomes negative x instead of positive x. And now the base here is 4. So when I flip this over, 1/4 becomes 4/1. 4/1 just simplifies to 4. So I'm flipping the base over. It becomes a 4 when I do that. And then I change the sign of the exponent because of that. And now both sides of the equation are exponents with the same base. And so the only way this equation can be true is for the exponents to equal each other. And so I'll take the negative x, the exponent from the left-hand side, set it equal to 3, the exponent from the right-hand side. And then I solve for x by dividing -1 on both sides, and we get x is equal to -3. And that's going to be our solution here. And that's the easy way to do the problem. All right, let's take a look at the next page of the exam. All right, so let me zoom in on that. And then I don't know if I'm going to do all of these in the interest of time. So I hope that's zoomed in enough. So we'll scroll up to question number 4. A deposit of $3,000 earns 8% annual interest. Find the amount in the account at the end of 10 years and the amount of interest earned during the 10 years if the interest is compounded. And then we have parts A, B, C, and D. I wish I didn't have to have the problem with that many parts. However, I'm constructing the exam from Math Excel. I have to use the problems that Math Excel provides. I guess there is a way to customize questions, but I haven't really looked into how that works. And in fact, we tried to do that with the honor statement that we are implementing for test on Math Excel. And you had to download Flash, which nobody uses anymore. So it's something I haven't really looked into. But anyways, I would be happy just having one of these on the test, but this is the way I have to give this problem on the test. And monthly would be the one I'd probably do. It's a really repetitive thing because they're all going to be the same. Just the numbers will be a little bit different each time. So students have seemed to manage okay with this. And it's a plug and chug problem. So it's not going to take a whole lot of computation, solving complex equations to, figure it out. You do need to know the formula. And the formula for compound interest is A equals P times 1 plus R over N to the NT power. I kind of hoped it would have that formula on the screen for you. It doesn't. So I'm trying to think. I'll try to include that on the test. I've kind of set up the test already, but I'll try to go back and somehow add that in so that you have that information when you take the test. But you might want to remember it just in case I'm not able to do that. All right. And so we plug the numbers in. And it's possible to memorize. I've had classes where I promise to give that formula during the test. Then I forget to actually write it on the board and nobody reminds me. And I still have students that do this problem just fine. So they remember the formula. So a deposit of $3,000, that's the principal. That's how much we're initially investing. Earns 8% annual interest. That's R. At the end of 10 years, that's T, that's the time. And so N is the only variable not mentioned up here in the initial paragraph. N will change depending on which part we're doing. So for annually, N is equal to 1. For quarterly, N is equal to 4. For monthly, N is equal to 12. And for daily, N is equal to 365. All right. I'm just going to do part C, because like I said, the other parts will go exactly the same, except the value for N will be different. Everybody seems to get part A correct anyways. That one people don't seem to have trouble with. But I do find students will sometimes get some crazy answers for part B, C, and D. Parts B, C, and D. I'm not sure what they're doing to get the answers they're coming up with, because they are like, there's no pattern to them that I could tell. Like it's, a much bigger number than you would expect. Like, part A, we're going to get something like $4,000 or $5,000, something more than 3,000, but not like, no, it might be more than that actually, but definitely less than $10,000. So that's what we get for part A. And then for part B, they would get something like $1 million and something. And so it's like this huge jump, which if you think about it, doesn't quite make sense. And then that just continues. And by the time they get to part D, it's like scientific notation, like 1 times 10 to the 30th dollars or something like that, which again is not a really a reasonable answer for the problem. So it's all about how you type it in your calculator, because on the paper they write down the right thing, right? They're going to have, so this is for part C right here. They're going to have A equals P, which is 3,000, times 1 plus R, which is 0.08, over N, which for part C is going to be 12, raised to the power of 12 times 10, right? N is 12, T is 10. And that's what they'll have on their paper. But then the answer just doesn't match what they have on their paper. So this is what we need to type into our calculator. So let's go ahead and pull up my crazy calculator that is a little bit hard to use. Hopefully your calculator is a little more user-friendly. So I'm going to type this in. Let me go ahead and make sure all of it is visible. So 3,000 times. Now on your calculator, you might not have to put the times there. You could just maybe start your parentheses. But this calculator I found, I have to put the times there for it to work right. So parentheses 1 plus 0.08. So remember, when you plug in your value for r, you need to convert it to decimal form, over 12, and then close the parentheses, right? Now, the calculation it just performed is the part inside the parentheses. It has not multiplied it by 3,000 yet. And that's good because we don't want it to, because the next thing we want to do is raise it to the power of 12 times 10, right? So the way order of operation works is you do parentheses first. So this is fine if they want to do the parentheses first. Then you do exponents, right? Then you multiply by 3,000. That might be one reason why students are getting crazy answers. Now that I think about it, they might be multiplying first and then raising it to this big power. That would give you some big numbers. Maybe that's what's going on. All right. Now, here's where I would have thought students would make a mistake. Now, when you raise it to the power, you don't want to raise it. You have to put parentheses here. Now, on paper, you don't, because it's clear when we write both of these in the air that they're both in the exponent. But when you're typing it in on a calculator, it's all going on one line. It's not going to know from the way you type it without parentheses that 12 and 10 are both supposed to be in the exponent. It's going to assume just the 12 is in the exponent, and then you want to multiply the whole thing by 10, which is not what we want to do. We want the 10 in the exponent as well. So you got to use parentheses here, right? And then 12 times 10. Close the parentheses. And that makes sure that both numbers are in the exponent, and the calculator is aware of that. All right, so hit enter, and we get this. So much bigger than I thought. I was thinking 4,000 or 5,000. It's actually closer to 7,000. So, and again, this is money, so we go to 2 decimal places whenever we're dealing with money. So $6,658.92. So 665892. Let's see if I can remember that. Okay. 669852. I think I got those numbers backwards. Let me look at it again. Yeah. 665892. Okay. 5892. Let's 5892. Okay, I think I got it right this time. Okay, so that is the final amount in the account after 10 years. And 10 years is a long time. That's why it got to be such a big number. For the interest, because it also wants us to find the interest on that investment, the interest is just simply how much more money do you have now than what you started with, right? We started with $3,000, so I'm going to subtract that away from this, and whatever's left is the amount of interest I've earned. And so that's how you find the interest. You subtract 3,000 in this case. Whatever you started with, that's what you subtract by. And so we'll get $3,658.92 as our interest. All right. And that's how you'll do parts A, B, and D as well. It's just the value of n will be different each time. All right. So let's move on to the next couple of problems down here. So for question number 5, find the logarithm. Now your calculator may allow you to type this in to get the answer. That is not the way I would intend for you to do this problem. In fact, I remember it used to be calculators couldn't do any other logarithms except log base 10 and natural log. And I remember the first time I found a student with a calculator that let them type in log base 9. And I found out because I had a student taking a test and they had like 3 different calculators while they were testing. And it made me think, like, why would you need 3 different calculators for a test? One should be enough. Well, they had one calculator that they were more comfortable with for doing most of their calculations. But it didn't have graphing on it. And so they had another calculator for graphing. And then they had another calculator to do the logarithms because their first calculator couldn't do it. So they had a third calculator where they could type in log base 9. And then when I found out, I was kind of disappointed because this is not an interesting question for me to put on a test if all you're going to do is put it into a calculator and get an answer. It doesn't show any knowledge whatsoever. So, however, I've kept it on the test. And so I'm hoping that you're not just plugging this into your calculator to get the answer, but that you understand what a logarithm is asking you, which is how many powers of the base does it take to equal this number inside the logarithm, right? So 9 is my base. How many powers of 9 does it take to equal 3? So that is the way this problem is intended to be done This is in section 4.2. We later in the chapter learn the change of base formula, which you could also apply here. And I'm okay with that because, again, it demonstrates some knowledge. If you're just plugging it into a calculator, that doesn't demonstrate any knowledge. But if you're changing the base to base 10, that's another way you could do this problem. So this one's kind of a hard problem because how many powers of 9 does it take to equal 3? Well, how do you get from 9 to 3 using exponents? A square root would get you there, right? And the reason we would think of a square root is because square roots can be written as exponents. So to go from 9 to 3, you would want to take the square root of 9 to get 3. Square root as an exponent is a 1/2 power. So log base 9 of 3 is equal to 1/2. How many powers of 9 does it take to equal 3? 1/2, right? Because you're taking a square root. And so that's the answer there. For question number 6, we're back to graphing. In this case, we're graphing a logarithmic function. So your basic log function, without anything else, just log by itself, with the same base. The base is 10, so I'll keep the same base here, base of 10. You should remember what that basic shape looks like. And it's actually all flipped around from the exponential function. That's a good way to try to remember what this looks like. So instead of the asymptote being the x-axis, the asymptote is the y-axis. And instead of having the point at 0, 1, you have a point at 1, 0. Right? It gets flipped around. And so what's going to happen is the graph is going to look like this. All right, so that's what your basic logarithmic graph looks like if the base is bigger than 1. What changes do we want to make to this particular graph? Well, let's start with this. The plus 3 is going to shift the graph. I always have trouble putting those two words together. Shift the graph to the left by 3. We know it's left or right because this is directly on the x variable. That's why I like to start with that one, because that's how I remember it is if it's being added or subtracted directly to x, that's going to either shift it left or right. And it goes in the opposite direction that your intuition would tell you, right? Plus 3 you would think would bump the graph to the right 3, but it actually bumps it to the left 3. And since this is not being multiplied to the logarithm, it's being added. And again, if you flip this around, it's like having a -2 at the end. That's going to shift it either up or down. In this case, it's going to be down 2 because it's negative. It goes in the direction that you would expect. All right, so let's try to recircle that. Okay, that doesn't really work either. So down 2 to the left 3, and then that's it. So those are the changes that we want to make to this graph. Now, shifting this graph up or down does not move the asymptote. The asymptote would stay on the y-axis, but shifting it to the left 3 is going to move the asymptote from x equals 0 to x equals -3. So now the asymptote will be located here. And in this particular problem, it doesn't ask you to specify what the asymptote is, but without having the asymptote in the graph, you're not going to draw the graph correctly. I see this very commonly where students will get these points here, they'll plot them, and they'll have some points that kind of look like this, and then they kind of draw it like, well, maybe not quite that badly, but they'll connect these points, but they don't realize there's a stopping point. They just kind of keep going to the left forever, but you can't do that. There's an asymptote that will block you from doing that. And so if you don't know the asymptote's there, it's going to show in your answer, right? So the asymptote's located here at -3. This point that was at 1, 0 will get shifted to the left 3 also. So it's going to end up at -2, right? We're starting at 1. Go to the left 3, we'll be at -2, and then down 2. So it's going to be at -2, 2. That's where that point's going to end up. Right. And then the graph is going to approach the asymptote without crossing as we go to the left, and it's going to really flatten out as we go to the right. And we can get a better sense of that by actually getting these points that we're supposed to get. I don't know why Math Excel, whenever you print a test into a PDF form or even into paper form, it seems to have trouble with organizing the elements of this problem, and the table for your points ends up behind the graph where you can't see it. So you have a couple of them here, which will really probably be enough, but if you wanted to, there's one more point that you're supposed to have here. If you want that one more point, you can pick any number you want as long as it's not less than -3. It can't be over here because the graph just doesn't exist over here. So pick any point, any value of x that you want over here. Because it's base 10, you can plug it into your calculator. So just pick a number. I'll just pick 4, for example. Anything will work. And so we'll plug in -2. Right, so let's see what that looks like. We'll have -2 plus log base 10 of -2 plus 3. Well, -2 plus 3 is going to be 1. And we've talked about this a few times, that log base 10 of 1, log base anything of 1 is equal to 0. Right, so that's just going to equal 0. So we get -2 plus 0, which is going to be -2. And that's the point that we already knew about from looking at the transformation, right? So we get -2 here. Let's plug in 0, right? So I guess I'll do this right here. So we have -2 plus log base 10 of 0 plus 3. And so that's going to give me -2 plus log base 10 of 3. How many powers of 10 does it take to equal 3? I don't know. There's not an easy answer for that one. But we can use our calculator, right? Our calculator can do log base 10. So let's go ahead and do that. So I'm going to plug in. I remember this calculator works backwards. Hopefully your calculator is a little more user-friendly. I have to type 3 first and then do log of that number. And that gives me log base 10 of 3. And then we're going to do -2. I'm just going to flip those around. So we did the logarithm first, and then I'll put the -2 after. It's a -2. So I'll just do -2 on that. And we'll get this. So -1.5. And for this table, for this chart, they only want you to round to the nearest tenth. That's the first decimal place. Because this is a 2, we will round this down to -1.5. All right. So -1. Try to make that my decimal, but it's a little bit too high up. -1.5. All right. So I have 0, comma -1.5. So notice how flat this graph is. All right. The bigger the base is, the flatter this graph becomes. Like the quicker it becomes flat. So it's a very sharp curve here, and it's going to be a really flat looking graph going to the right. It's never completely horizontal, but it's just going to look really, really low. We could do one more point. So let's plug in 4 here. If I plug in 4, let's just do this mentally. We'll get 4 plus 3, which is 7, right? So I'm going to do the same thing I just did, except with 7 in my logarithm. So we'll have, we'll clear this out. Start with 7, take the log of that, and then we'll subtract 2, and we get -1.2 if I go to 1 decimal place, right? So -1.2, which again still hasn't reached -1 yet. So even when I go way out here, it's still going to be below -1 on the y-axis. You don't reach -1 until you plug in 7 here, right? Because for base 10, the next nicest number that you can get is if you plug in a 7. So if I were to plug in 7 for x, I get 7 plus 3 here, which is 10. Log base 10 of 10 is 1. Right? How many powers of 10 does it take to equal 10? The answer is 1. -2 plus 1 is going to give me -1. Right? And so I won't reach 1 until I get this far out. And it's even worse after that. The next best number you can get would be having 100 here, right? For log base 10, 100's a good number to have, right? Because 100 is 10 to the second power. You don't reach 100 until you plug in 97 for x. So when you plug in 97 for x, then you'll get 100 inside of the logarithm. How many powers of 10 does it take to equal 100? The answer is 2. -2 plus 2 is going to give you 0. So we won't reach the x-axis until we go way, way, way out here at x equals 97. Right? Once we reach 97 on the x-axis, then we have reached the x-axis on our graph. Right? It's going to be very, very far out. And so you can see how flat that's going to be. All right. But we don't need that information. Just thought you might find that interesting. And so this is what it's going to look like. From here, it's going to approach. Oh gosh, okay, I'm doing a horrible job. My writing tablet's kind of sideways too. That's not helping. Okay, that's too directly down. So it's going to look something like this. I've done kind of a bad job there. And then it's a pretty sharp curve here. Oh, I missed that point. Let's try it one more time. Pretty sharp curve. It's kind of like, you know, even though I can see it writing on the screen, It's a little bit like doing it blind because I can't see it on my writing tablet. So that's kind of why it's awkward for me to connect points and draw things in straight lines and whatnot. Okay, so that's what the graph looks like. Once you have the graph, it's easier to figure out the domain and range. How far to the left? Well, there is a limiting factor here. I don't know if that's really the right... I was trying to see if there's a better word I could use, but there is something limiting our movement to the left. It's the asymptote, and it's not going to allow me to cross -3. And so I can't go any further to the left than -3. And in fact, I never even reach -3. It goes to -2.999999, but it never actually reaches -3. How far to the right does it go? Infinity. All right. That's the domain. The range, how far down? That's pretty clear. It's going to go down forever, -infinity. How far up? Well, this is, like I said, it's really flat, but it does continue to inch upwards as you go to the right, and it does that forever. So it's going to go up forever. It just does it very, very slowly. All right. And so that's the range. Okay. Let me see what time it is. Okay. I have to be done at a certain time, so I might have to pause this and resume it later. Of course, that won't mean anything to you because you won't be able to tell unless I look different or something because I'm doing it on another day. So anyways, I'm sorry for all the commentary. I should just focus on the math. So let me keep working on that. All right, so let's go to the next page. There's a lot of problems on this page. Well, let's zoom in first. So I'll zoom in a couple times. Hopefully that's enough for you to be able to see it. All right, so question number 8. For the following, find f to the -1st power. That means find the inverse function. So this is something else we'll learn to do in section 4.2. We want to use the switch and solve method. You start by replacing the function notation with the y variable. So we're going to have y equals 6 to the x plus 5 power. The second step is you switch x and y. So everywhere there's a y, you put an x. And everywhere there's an x, you put a y. So that's the second step. So step 1, step 2, step 3, and this is where all the math occurs. You have to now solve this for y. We talked about in section 4.2, one way of doing that, and the way you want to use here, is to convert this to logarithmic form. Right? So if you're trying to solve for a variable that's stuck in the exponent, convert it to logarithmic form. That will bring it down out of the exponent. The way you convert this to logarithmic form is you start by writing log. The base is the base, right? So the base is 6 for the exponent. That will be the base of my logarithm. I like to skip over this part for the moment, put an equal sign here. The logarithm equals the exponent, right? So this is the exponent. That's what the logarithm should equal. And so by elimination, what goes inside the logarithm is x, right? That's what we have left that we haven't addressed yet. And so that's converting it to logarithmic form. Now I can solve this for y by subtracting 5 to the other side. It does not go inside the logarithm. You're going to keep it outside the logarithm, but just kind of tack it on to the end. And so I'm going to have log base 6 of x minus 5 equals y. And then the last step is to rewrite the y using this function notation. Right? Didn't do a good job of circling that. And so I'm going to rewrite y as f inverse of x. And I'm also just going to flip this around. So I'm putting y on the left-hand side. I'll put this on the right-hand side. Log base 6 of x minus 5. All right. And there's our inverse function. All right. Question number 9. Rewrite this as a single logarithm. So we want to combine these together into one logarithm. And so since we're adding here, what I'm going to do is write this as one logarithm. And I'll take the 6 and the 4, and when I put them inside of the same logarithm, I will multiply them together. This will become 6 times 4 when they're placed inside of a single logarithm. And that's just how logarithms work. So if you're adding two logarithms together, you can add them into a single logarithm, but you multiply what's in those individual logarithms together when they're in the single logarithm. So this will be 6 times 4, which is going to be, of course, 24. And so that would be the answer here. So really quick, short problem, but you got to know how these logarithms behave. And if you don't, you're not going to be able to get the right answer there, even though it's not a lot of work to get. All right, for question number 10, rewrite the expression as a sum or difference of multiple logarithms. This is the reverse process. We want to expand it out into as many separate logarithms as possible. The shortcut for this one is to take each factor in the numerator and the denominator. So 31 is the factor in the numerator. It's the only thing there. We have 4 in the denominator as a factor and y as a factor. We want to separate those two because they're being multiplied together, but we want them to go into separate logarithms. And so I'll have log base 2. I'll put 31 inside of its own logarithm. I'll put the 4 inside of its own logarithm. And I'll put the y inside of its own logarithm. Then we have to decide whether these logarithms should be positive or negative. If it came from the numerator, 31 came from the numerator, that logarithm will be positive. So I'll just keep that as a positive, log base 2 of 31. If it's from a denominator, that logarithm should be negative, right? So 4 is from our denominator, which means this logarithm should be negative. This is to reflect that if you're dividing, you want to subtract your logarithms, right? If you're multiplying, you add the logarithms together when you split it up. But if you're dividing, you want to subtract the logarithms. We're also dividing by y, so we also want to be subtracting this logarithm as well. And so y is from the denominator. That means that logarithm will also be negative. And so this is how you expand it out. Not every problem will have this, but this particular problem does. You can simplify this logarithm here. So sometimes you can, sometimes you can't. So you just have to kind of look and see, does the base kind of work well with this number here? In this case, how many powers of 2 does it take to equal 4? Well, that's something that we can figure out pretty easily. It's 2, right? So I'm asking myself again here, how many powers of 2 does it take to equal 4? And if there's an easy, good answer for that, then you should simplify that logarithm. If this was like a 5 here, how many powers of 2 does it take to equal 5? There's not a good, easy answer for that one, so I would just leave it as a logarithm. Like this one, I'm making up a different example. We actually have one in the problem, right? How many powers of 2 does it take to equal 31? There's not a good, easy answer for that, so we'll just leave it as a logarithm. All right, so that'll stay as a logarithm. And this one has a variable, so there's nothing else we could have done with that anyways. So this would be your final answer in this case. All right, let me scroll down. All right, so number 11, rewrite the expression as a single logarithm. So in this case, we want to recombine them back together like we did on question number 9. This one's a little more complicated, right? We have a number outside the logarithm as well, but the shortcut here that I like to use is we're going to write this as one logarithm. So I'll just start by writing that one logarithm first. The base is going to stay 7. Anything from a positive logarithm goes in the numerator. It's just the reverse of what we just did, right? This logarithm's positive. That means x to the 9th power should go in the numerator. Sorry about that. I'm pushing the button to erase by accident. And x to the 3rd power is in a negative logarithm, and so it goes in the denominator. So anything in a positive logarithm, you put that in the numerator when you're combining it together. Anything in a negative logarithm, you put that in the denominator. And then any numbers outside the logarithm become powers inside of the single logarithm. So this 4 is going to be brought back in here and become a power on this x to the 3rd power. And so we're going to raise this x to the 3rd power to the 4th power, right? Which means we will multiply those numbers together, because whenever you have one power raised to another power, you multiply. So we'll have log base 7, almost said 10, log base 7 of x to the 9th power over x to the 12th power. Whoops. Sorry, I'm really having trouble avoiding pushing that button now for some reason. Okay. Because these are both x's, they have the same base, we can simplify this by subtracting the exponents. So our final answer here should be log base 7 of x to the negative 3rd power. And I think it's okay to leave it with a negative exponent for this situation. So, all right, so 9 minus 12 would be negative 3. That's how I got that. And again, I'm sorry that this is kind of hard to read here. This is a 12. I'll just write it over there. Okay, now here we want to find what this is equal to. We want to evaluate it. How many powers of 1/4 does it take to equal 9? Again, there's not a good, easy answer for that. If you have a calculator that lets you type in whatever base you want, again, this is a silly problem to have on a test, because if all you have to do is plug it into your calculator to get the answer, that's not really a very good test question. It doesn't test you on any kind of knowledge. So if you have one of those calculators, okay, this is going to be an easy 5 points for you. But the way you're intended to do this is to use the change of base formula, right? And the way the change of base formula works is I can change this logarithm from base 1/4 to base 10. The catch, though, is that I have to divide by another logarithm of the same base. So whatever base I choose here, I'm going to have that base both on the top and the bottom for both of these logarithms. So I'm going to choose base 10 so that I can plug it into my calculator. So you still have to use a calculator to do this problem, but most calculators only have log base 10 and natural log, and in those cases you have to change this base of 1/4 to a base that you can actually plug into your calculator. All right, so I'm changing it to base 10. The pattern here is that whatever was in the original logarithm, which is 9, stays in the logarithm on top, and then the base of the original logarithm goes in the logarithm on the bottom. And the new base, like I say, could be anything you want. We're going to choose base 10 so that we can plug this into our calculator. All right, so we're going to have log base 10 of 9. So I'll start by doing 9, log base 10 of that, because that's the way this calculator operates, divided by, well, this one's going to be kind of tricky. How do I want to do this? I guess like this. 1/4, because it's a fraction. And we'll take the log of that. Let's see if it cooperates. Okay, great. Okay, so it does the right thing here. So we have log base 10 of 9 divided by log base 10 of 1/4. So I'll hit enter to see what that is equal to. And I get, this is a really common answer. I don't know if this set of numbers is pretty frequent, but I feel like this answer comes up a lot. Negative 1.58. Now they want us to round to the 4th decimal place. And so we have a 6 here on the 5th decimal place, which means we want to round this up. But the 9, when you round it up, it rolls over to 0, and that means we have to bump up this decimal place as well. So it's going to be negative 1.5850. 49 gets rounded up to 50, if you will. All right, so negative 1.5850 is what that is approximately equal to, right? That's an approximation. All right. So let's keep going here. Number 13, solve the equation. And number 14, also solve the equation. So now we're in the territory of section 4.4. If your equation only has one logarithm, you solve it by converting it to exponential form. And the way you convert it to exponential form is to do the loop, right? So you start with the base of your log, which is 2. That'll become the base of my exponent. Raise it to the power of whatever's on the other side. Kind of covered it up, but it was a 4. And then set that equal to whatever's inside the logarithm, which is going to be x squared plus 7. Right. So you convert your logarithmic equation into an exponential equation. Right. And then, now that x is no longer stuck inside the logarithm, you can now solve this equation for x. We have 2 to the 4th power, which is 16, equals x squared plus 7. Because we have x squared, this is technically a quadratic equation. However, since all we have is x squared, we don't have any other x's anywhere else, we can just solve this like usual, right? Get x by itself. We'll subtract 7 from both sides. So we'll get 9 over here. So we get x squared is equal to 9. And then we take the square root of both sides, and we get x is equal to 3. And don't forget the all-important detail of plus or minus whenever you take the square root of both sides of an equation. So really, we have 2 solutions, positive 3 and negative 3. All right, so that's all there is to number 13. For number 14, it's really going to be very similar, except there are going to be a couple of differences. I was trying to kind of cut off the space there, but I really did a bad job. So I think I'll just, I don't know, it kind of does bug me. I feel like I want to have a boundary here, but I can't seem to draw straight across once I get to the second half of the screen. Okay, that's going even worse. Okay, there we go. Okay, that worked better. Okay, so it's going to be very similar to question number 13, but the first thing we have to do to make it similar to question 13, because we have two logarithms here, is we want to combine those into a single logarithm like we did earlier on question number 9. We are adding these logarithms together, so I can add them into a single logarithm. It'll be log base 3, same base. And I'll take the x plus 12 and the x minus 12, and when I put them inside of the same logarithm, I will multiply them together. Because we are adding these logarithms, the x plus 12 and the x minus 12 should be multiplied when they go inside of the same logarithm. And so I'll have x plus 12 times x minus 12. And because we're multiplying, I got to put some parentheses around these two things. And because I'm using parentheses on these, I want to use brackets for the logarithm to show what's inside the logarithm. You don't have to. You can keep using parentheses like we normally do with like here, right? Log base 10 of 9, I use parentheses here to show what's inside the logarithm. You can keep doing that here, but then you get parentheses on top of parentheses. It's a little bit harder to read. So brackets just a little bit nicer to look at. It's still equal to 4, right? And now that I have just one logarithm, I proceed the same way as I did in number 13. Right? I'm going to convert this to exponential form by doing the loop. So I'll take the base, which is 3, raise it to the power of whatever's over here, which is 4, set it equal to what's inside the logarithm, which is x plus 12 times x minus 12. Now I can solve this equation for x. I'll start by multiplying all this stuff out. And so we have 3, I'm sorry, just 1 second. Let me kind of get situated here a little bit better. 3 to the 4th power is going to be 81. Here I'm going to FOIL, so I'll get x squared minus 12x plus 12x minus 144. These numbers are looking really familiar. I think these are the exact numbers we had in a problem in section 4.4. I think one of the examples I did there worked out the same way. I want to say almost exactly the same. The minus 12 and the plus 12 cancel out. Well, and so we're back to the same scenario we were here. We just have, it's a quadratic, but all we have is x squared, so we can just solve it for x. We'll do that by adding the 144 to the other side. We get 225. That's the number that rings a bell to me. So we get x squared equals 225. We solve this for x by taking the square root of both sides, and we'll get 15 is equal to x. Because I took the square root of both sides, I'm supposed to do plus or minus. Now, one other difference between number 14, so there's two things that are different between 13 and 14. One difference we already dealt with. You have to take your two logarithms and rewrite them as a single logarithm. Then the problem kind of works the same as number 13 from that point until you get to the end. Once you get to the end, you have to check these answers. You cannot trust those to be correct for the original equation. They are definitely the correct solutions here. Sorry, let me try that again. They are definitely the correct solutions to this equation, but that's not the equation we were given. We were given this equation. I want to make sure they will work here as well, and there is a danger that they might not. So whenever you're doing this operation of combining logarithms together into a single logarithm, your equation's like 95% the same, right? So these two equations are like 95% similar, but they are slightly different from each other. There are numbers that will work here that will not work here. And that's what we have to be worried about with our solutions. So the other difference between 13 and 14 is you have to check these answers. So let's check 15. We'll get log base 3 of 15 plus 12 plus log base 3 of 15 minus 12. And that should equal 4. And so 15 plus 12 is going to be 27. How many powers of 3 does it take to equal 27? The answer is 3. Right? And so that's what that logarithm is equal to. Here, 15 minus 12 is going to be 3. How many powers of 3 does it take to equal 3? The answer is 1. So that logarithm is equal to 1. 1 plus 3 equals 4. It works out. Right? So 15 is good. Negative 15, however, is going to be a problem. So let's do that down here. Let's see if I can draw another boundary. Okay. So we'll have log base 3 of negative 15 plus 12. And there's more. This is what I did in the video. This is all, I just recorded the video yesterday too, and I'm still a little bit foggy on my memory with that, so I forget things pretty quickly. But I do remember this part, which is I didn't write out the rest of the equation, and I'm going to do the same thing here because this already is a showstopper. Negative 15 plus 12 is going to be negative 3. And so we're going to have log base 3 of negative 3, which is undefined. It's like dividing by 0. You can't take the logarithm of a negative number. Doesn't matter what the base is. It doesn't work. It's undefined. So negative 15 does not work in that original equation. And so we have to throw that one out. So only positive 15 works. That's our only solution here. On the test, when I'm looking at your work and I'm grading your work, if all you have here is 15 and you don't show me you had plus or minus, and you don't show me that you checked your answers, even though technically you're right, the only answer is 15, since you don't have that extra detail about how you confirm that, I'm going to take points off for that. So make sure you're showing me that when you take the square root of both sides, you do get plus or minus, and that you checked the negative one, and that's why you threw it out. That's why it's not there. You need to show me that work. Don't just, assume it all without writing it down. I want to make sure you understand that concept. So make sure you're acknowledging it on your test. All right. So I think this is the last page. So let's zoom in a couple times and then scroll up. And it's a doozy. Got quite a few tough problems here. And I'm sorry, this video has already hit an hour. I feel like I didn't rush as much as I normally do. And again, I did a little bit more commentary than I should have. So I apologize for the length of the video, but just a few more minutes. I think I have the time. I have like 20 minutes left before I need to go do something else. All right. So solving this equation, it's a single exponential equation. And we want to be able to approximate it. So it wants us to round to 4 decimal places. It has the squiggly equal sign, which means we don't want the answer in logarithmic form. We want the answer in decimal form. So I want to be able to plug it into my calculator. Now, if you have a calculator that lets you type in whatever base you want, you can kind of do this problem the same way we did the inverse function. You can just convert this to logarithmic form. It'll be log base 4, right? Because the base will still be the base. And then you can just plug in the log base 4 into your calculator and you'll be fine. You'll get the decimal that way. But for the rest of us that don't have a calculator that can do log base 4, we have to make sure we're getting log base 10 or natural log. So the way we're going to approach this equation is to apply a log base 10, or a natural log if you prefer that one, to both sides of the equation. So I will apply log base 10 to the left-hand side, and I will apply log base 10 to the right-hand side. So the bases here don't match up, but that's okay because this property of logarithm still applies, which is if you have an exponent inside of your logarithm, you can bring it down and multiply it in front of the logarithm. So it's going to allow me to bring the exponent from inside, how do I want to say this? It's going to allow me to take the x that's stuck in the exponent, bring it down to the ground level where I can solve for it. Gets it out of the exponent, gets it out of the logarithm, down where I can actually solve for it. Right. So any base will allow me to do that. So, log base 100 would let me do the same thing. It's just that I don't have a button on my calculator for log base 100. So I'm using log base 10 because that's what's on my calculator to use. Right. Any base here would work. It lets me bring the exponent down, and I'll get x minus 1. Because there's 2 terms, I need to keep that in parentheses. And what I'm left with here is log base 10 of 4. And that's still equal to log base 10 of 7. So now I can solve this for x, now that x is down on the ground level. The way I recommended doing this in section 4.4 in that lecture video is getting rid of this logarithm by dividing it to the other side, right? It's being multiplied to this parentheses, so I can cancel it out by dividing it to the other side. So I'll divide by log base 10 of 4. These cancel out. And I guess I'll continue up here. I'll get x minus 1 left over here. Because the logarithm is gone, I don't need the parentheses anymore. So I'll just put x minus 1 without parentheses. Equals log base 10 of 7 over log base 10 of 4. Right, and then I can finish solving for x by adding 1 to the other side. And so I'll get x equals log base 10 of 7 over log base 10 of 4 plus 1. This is still an exact solution. And I recommend waiting until you get to the very end and you've solved it for x before you get the approximate solution. So I kept it exact as long as I could. Now that I'm done solving it for x, let's just redo that. I can plug this into my calculator to get the approximate answer. So again, using the calculator, clear this out. What do we want to type in here? So we'll have log base 10 of 7 over log base 10 of 4, and then plus 1. And so that's the calculation I just did, which is what's on my screen. And this is the result I get, rounded to 4 decimal places. So that would be this decimal place here. Because this is a 7, I will round this 6 up. So I'm going to round it up to a 7. So I get 24,037. Let's see if I can remember that. 24,037, was that right? I think it was right. Yeah, 37. Okay, I was thinking maybe it was 67 instead. All right, and then the decimal place goes here. All right, so it's 2.4037. All right, so that's how you solve that equation. For number 16, solving an equation with 2 exponential expressions, you're going to use the same strategy. You will use a logarithm to get these exponents down to the ground level. You'll choose log base 10 here because you can plug that into your calculator, but also because you can't use the trick that you can use in number 15. So if you have a calculator that lets you type in whatever base you want, you can get away with that on number 15. You can use log base 4 and just convert it to logarithmic form without having to do this extra work. You can't really get away with that here because there's 2 different bases. So which base would you use? Are you going to do log base 15? Or are you going to do log base 5? And whichever one you use, it's still going to be a mess when you convert it to logarithmic form. And so you really have to do number 16 using this technique. Apply a logarithm to both sides. Since there's 2 different bases, you might as well just use log base 10, get the exponents down to the ground level, and then you can solve it from there. So I'm going to apply a log base 10 to the left-hand side, and I'm going to apply a log base 10 to the right-hand side. All right, and that lets me take my exponents from inside the logarithms, multiply them down in front of the logarithms. And so I will have x times log base 10 of 15 equals, parentheses this time because there's 2 terms, x plus 1 times log base 10 of 5. This time we can't use this method of just dividing the logarithm to the other side to clear the parentheses, because it's just going to make this side more difficult to deal with. Here it wasn't a problem because we're just trying to shove everything over to the right-hand side to get x by itself. But here we have to kind of deal with having 2 different x's. And if you're shoving this over here to the left-hand side, you're just making this x worse. So you're making this x better, but you're making this one worse, and it's going to be an issue later on anyways. So the best way to manage this one is just to go ahead and distribute that logarithm into the parentheses. So we'll still have x times log base 10 of 15 equals x times log base 10 of 5 minus, not minus, why did I say minus? Plus 1 times log base 10 of 5, which of course the 1 doesn't have to be written, but just to make it clear like what's happening there, I'm gonna write it at this point, but then later I'll go ahead and absorb it into that logarithm, right? Because 1 times anything is just that anything, right? The 1 doesn't have to be written there. All right, the next step is to get your x's together on the same side of the equation. So I'm going to subtract this x log base 10 of 5 to the other side of the equation, and leave this one over here by itself. So we'll have, I'm going to continue up here. Hopefully this is not going to get too messy. We'll have x times log base 10 of 15, that was already here, minus x log base 10 of 5 equals 1 times log base 10 of 5, which is just going to be log base 10 of 5, right? The 1 doesn't need to be written anymore. And then what you do with this is you factor out the x, right? It's a common factor in both of these terms, so I'm going to factor it out as a common factor. What I'm left with is log base 10 of 15 minus log base 10 of 5 equals log base 10 of 5. All right. And from here, you could go ahead and just go right to getting the solution by dividing this to the other side. I have some students that do the problem that way. But you can make this a little bit easier on yourself by combining these logarithms together first. Because we're subtracting, when I put the 15 and the 5 inside the same logarithm, I will divide them, right? So this will be log base 10 of 15 divided by 5, which normally I would write out, but I'm kind of running out of room, so I'm just going to go ahead and write the result, right? So I'm taking, maybe I could write it out somewhere else. So I'm taking 15 over 5 inside of that one logarithm, right? That's how I'm combining those together. 15 divided by 5 gives me 3. And then the x just gets copied down, equals log base 10 of 5. So this is kind of, funny to me, I guess, if math can be funny. Because look how complicated this was, right? I mean, the equation doesn't look too complicated, but just the process is fairly complicated. We have to do logarithms, do all this crazy stuff. And then when you get to the end, it's this really simple answer, So you divide by log base 10 of 3 on both sides. And you get x equals log base 10 of 5 divided by log base 10 of 3. And that's it. And so you plug that in. Well, I shouldn't say that's it. You plug it into your calculator. They, for some reason, aren't using the squiggly line here, but they do tell you they want 4 decimal places. So we plug that into our calculator. But like I said, it's a really simple expression to get from that really complicated process, which for some reason seems a little bit humorous to me. Because I feel like life can be like that sometimes. Like we go through all these complicated things in life, and when really things were really simple all along, but we made them more complicated than they had to be. I mean, in this case, we had to do it this way. It had to be this complicated, but let's see. Okay, I'm trying to cut that off from the other problem so it's easier to read, hopefully. All right, so we're going to type this into the calculator real quick. So 5 log base 10 of that divided by 3 log base 10 of that, and that's equal to this. So we'll get 1.4650, right? Because again, same thing we saw earlier. I don't know why this happens so often. 50 seems to be a very common ending to a lot of these answers, but the 7 is going to make me round that 9 up to a 0. That makes this 4 bump up to a 5. So it's 4650, right? 4650 is, I guess, I don't know if I can squeeze it in right there. Pick a different color. 4650. All right, and that's the approximate answer, and that's what you want for this problem. Okay, so I was feeling like I had plenty of time. I'm down to 10 minutes left before the thing I need to go and do. I don't know if I can get through both of these problems in 10 minutes. They're word problems. Now, 18 is really not that bad, but 17, it's going to take a little bit of time. But I guess let me try. All right, so 17. Prehistoric cave paintings were discovered in a cave in France. The paint contained 36% of the original carbon-14. The half-life of carbon-14 is 5,730 years. Estimate the age of the paintings. The formula that you want to use is this formula here for radioactive decay. It's another one that kind of wish was embedded in the problem. It's not. I'll try to see if I can provide that formula to you somehow when you're taking your test. And so I'll look into that either today or tomorrow. Another way you could write this formula, though, and the way that would be more, so if they give you the amount remaining as a percent, a better way of structuring this formula is to divide the a sub 0 to the other side. So we get a divided by a sub 0 equals e to the RT, where this ratio, this fraction, will represent the percent remaining. And so that percent really replaces 2 variables at once, which is a nice way to look at it, and it saves you some time. Right? So the first thing we need to do before we can answer this question about the 36% is to find r. Right? So the half-life is given to us so we can find what r is equal to. So we'll do that right here. For half-life, 50% is remaining. And so let's go ahead and write that out. 50% remains. So using this formula, I'll have 50% remaining after 5,730 years, right? That's the time when 50% is remaining. And then I can solve for r to find out what r is equal to. So we do, in this case, it's like the exponential equations we were looking at just a while ago, except in this case, we will want to use natural log because it matches the base of our exponent. So I'm going to apply a natural log to both sides of this equation. All right. And then natural log cancels out with e because the bases are the same. Natural log is log base e, the exponent is base e, they cancel each other out. So I'm going to get natural log of 0.50 equals r times 5,730. Now I can solve that for r by dividing the 5,730 to the other side. And I'm going to get natural log of 0.50 over 5,730 as my value for r. All right, now you can plug that into your calculator. If you go back to the video I did for section 4.4, I did that, and you get negative 1.2 something times 10 to the negative 4. So it's a pretty small number. However, you don't want to round that number off. So you want to keep all the decimal places. Don't stop at negative 1.2. That definitely would give you the wrong answer if you rounded it that much. Excuse me. Instead, what you want to do, I guess what you could do instead, so you could go ahead and plug that into your calculator, get this decimal number, and just keep all those decimal places when you go to the next part of the question. But what you could do instead is just leave it like this. This is exact. You don't have to worry about rounding. This is the exact value for r, and just use that over here. This is something that I find more and more of my students doing on their exams, is they'll leave their value for r like this, and they don't even write it over here. They just kind of point an arrow and say, that's what I'm using for this value of r, without actually even writing it out, right? So now we're ready to answer this question about 36%. So we'll go ahead and use that as our percent remaining. So that'll be 0.36 here equals e to this value of r. A lot of students will go ahead and write it in like this. Even though it looks complicated, it actually is easier than having all those decimal places to deal with, times t, right? Which is what I'm trying to find. How long is it going to take for us to have 36% remaining? And then I can solve this for t in the same way as we did for r over here. We're going to do natural log to both sides. So we'll have natural log of 0.36 equals the natural log of e to this thing, I'm going to go ahead and cheat there, times t, just like before. Let me see if I have any more room down here. Okay, I do have a little bit more. That's nice. Okay. The natural log and the e cancel each other out. Let me switch colors here to make that easier to see. So these cancel each other out. So I end up with natural log of 0.36 equals the natural log of 0.50 over 5,730 t. And now I can solve that for t by dividing this to the other side. Natural log of 0.50 over 5,730 divided to the other side. Now, when you go to type this into your calculator, you have to be careful because I wanted to make sure I'm dividing by this whole expression. On paper, it's pretty clear that this is what's in the denominator and this is what's in the numerator. But when you're typing it out on a calculator on the same line, it's not as clear. So we have to make sure to use parentheses when we're typing this into our calculator. Put parentheses around the denominator to show the calculator that this is the whole thing I'm dividing by here. All right, so let's go ahead and do that real quick, and then we'll have our answer and we'll get to that last problem. All right, so we have 0.36, natural log of that, divided by parentheses, because I want to put this in parentheses. Now to do my natural log, I got to do 0.50 first. That's just the way this calculator works. Natural log of that, divided by 5,730, close the parentheses for the denominator, right? And this is giving me that value for r that I talked about, negative 1.2 times 10 to the negative 4. That's the denominator part. But to do the complete calculation, I'll go ahead and hit enter, and I get this result. So 8,445 years, right? I'm not sure, I kind of lost the directions there. Round to the nearest integer. So we just want to round it to the nearest whole number. So let me scroll back down, and then pull that number back up because I forgot already. 8446, right? Because we're going to round that up because of this 6 here. The 5 gets rounded up to a 6. 8446. 8446 is the approximate number of years it would take for that amount of decay to occur. All right, last problem. Sorry this video went on a little bit longer than I would have liked, but want to make sure you are as ready for this test as possible, so I wanted to go through every problem in detail. And that way, in case you didn't have time to watch all of my individual lecture videos, hopefully you get a good sense of how to do these problems just by watching this video. All right, so for this last problem, the sound level L in decibels, right, so that's the units of L, it's not a variable, is given by the formula L equals 10 times log base 10. The worst part about this problem here, that's an I times 10 to the 12th power. That's scientific notation. And then this is also a bad part of the problem. Decibels, which is the units, which is not a variable. It's not part of this formula. So it really is kind of misleading to have that there. So I would just ignore it. All right, this is your formula right here that you want to use, where I is the intensity of the sound in watts per square meter. The sound level is 90 decibels, right? That's the sound level. I get students that get confused about where to plug that 90 in, but I think it should be clear for a couple reasons. One reason is it says sound level is L, and this is the sound level. So that's L. Also, the question here, what value of I gives you a sound level of 90 decibels? It makes it clear you're looking for I. This must be L then, right? So I'm going to take this formula. I'm going to plug 90 in for L, right? So we'll get 90 equals 10 times log base 10 of I times 10 to the 12th power. Right? And then I'm going to solve this for I. It's stuck inside of a logarithm, so our rule of thumb for solving a logarithmic equation is to convert it to exponential form by doing the loop, but you can't do that unless the logarithm's by itself. So you can't do the loop yet. I have students that will. They'll take the 10, raise it to the 90th power. It doesn't work because it doesn't account for this 10 properly. So we need to get rid of the 10 before we can do the loop. It's being multiplied to the log, so to get rid of it, we will divide by it. Divide by 10 on both sides, we get 9 equals log base 10 of I times 10 to the 12th power. Now we can do the loop, right? You start with the base of the log, which is 10, raise it to the power of 9, so we get the base of my log becomes the base of my exponent, raise it to the power of 9, and set that equal to, see, I'm not sure if it's going to work with my webcam being there, so let me just scroll. Set it equal to what's inside the logarithm, right? That's what I'm trying to get to. So we have I times 10 to the 12th. Now we can solve for I by dividing. This is one of the only cases I've ever seen in an algebra class where X is actually multiplication, right? It's, again, there, it's written in that way because it's like scientific notation where we commonly use X for multiplication. But I don't know, you don't normally see that in a formula like this, but it literally means multiplication. So to cancel out that 10 to the 12th power, we will divide by 10 to the 12th power. Cancels that out. We get I equals, here we can simplify because they have the same base, so the base will stay 10. You subtract the exponents. 9 minus 12 is going to be negative 3, and that's a really great way to leave the answer. But you could also plug this into your calculator, and you would get 0.001, which is also okay. So I'm okay with the answer being either way. And that concludes the review of exam 4. So you will be taking this exam hopefully pretty soon. And if you're one of my students, if you have any questions, please contact me. Good luck with exam number 4.